Hello everyone, this is Edward Doolittle here with your Stat 100 lecture for Chapter 9. I'm going to break this up into a few pieces. So today we're just going to do, or this lecture we're just going to do 9.1 and 9.2. That's just an introduction to the topic, large sample tests of hypotheses. So this is kind of the evil twin. I shouldn't say evil. It's the twin of Chapter 8. So Chapter 8 and Chapter 9 essentially use the same information about a situation. They just present it in a different way. So it's mostly the same kind of information. It just presented in a way that is kind of science-oriented here in Chapter 9. But both of them are used commonly in many applications, so we should be familiar with both of them. And there are a few additional topics that we're going to cover in Chapter 9 as well. So anyway, let's get started. So what we're talking about in Chapter 9 is hypothesis. And then the plural is hypotheses. It's a Greek word. So hypothesis is something, it's something that you don't know whether it's true or false, but you make a statement that it is true. So, you know, you may be well, you may have something in mind. Say, let's take a look at a courtroom example. So the defendant is guilty versus the defendant is not guilty. And if I say the defendant is guilty, I'm making a hypothesis. If I say the defendant is not guilty, I am also making a hypothesis. And one or the other of those is true. But we're not sure which it is until we go through the trial process. So that's kind of the prototypical example of a hypothesis. So, there are famous hypotheses in mathematics. There's the Poincare hypothesis, which is a statement about spheres, about certain properties of spheres, and it wasn't known whether it was true or false, but Poincare, a mathematician, believed it was true, so stated it as a hypothesis. He didn't state it as a theorem. That's when we know something is true, but he stated it as a hypothesis. And so when you believe something is true, you can state it as a hypothesis, but then you still have to go through some kind of test, some kind of trial, say, to determine whether a hypothesis is true or false. So that's a general idea of a hypothesis. Now, when we do a statistical test of hypothesis, what we're going to have is something we call, kind of strangely, but this is the name that has stuck, the alternative hypothesis. And typically, this is what we want to show to be true. It's something interesting. It's something usually worth publishing if we discover that it is a true statement. And so it is something different from the status quo often. It is what the researcher wishes to establish. And that, I guess, might be the origin of the term alternative. So hypothesis is a capital H, and then the little alternative hypothesis is a little subscript A. That's actually the main thing. Now, the textbook, when it lists these things, it lists this one first. This is the null hypothesis. So it's got a little zero there, H sub 0. And the null hypothesis is the kind of the contradiction or the opposite of the alternative hypothesis. In some sense. We'll get to the details in a second, but the general idea is that it's the opposite of the alternative hypothesis. So back to our courtroom drama here. Typically, we want to establish that somebody is guilty. That would be the alternative hypothesis, and not guilty would be the null hypothesis, sort of the status quo. If we didn't have any evidence, we certainly wouldn't assume that somebody was guilty. So the status quo is the null hypothesis. And I guess what we say is innocent until proven guilty. So that's another way to think about the null hypothesis, is that it's innocent until proven guilty. And the alternative hypothesis is guilty. And that is certainly something that's interesting. It's certainly something that's worth publishing. So that's the general idea. Now to do the trial, so to speak, what we're going to do is to calculate a test statistic. And the statistic, we should remember from the very beginning of this course, is a number computed from a sample. So there's nothing new there for the word statistic. I'm just reminding you that it's a number computed from a sample. And associated with the test statistic is something called a p-value. And a p-value is a probability. What we want to do is to find test statistics if they are, whether they're a very low probability or a high probability result. That's really what we want to determine, and that will determine about whether we are going to, which hypothesis we're going to support. Now there's one other related topic called the rejection region. And that is associated with the test statistic, and it's really kind of an alternative between the p-value and the rejection region. I will get into all the details about this in a minute, so don't worry too much about it right now, but if we're using test statistics, we're going to be using rejection regions, and if we're using the p-value, we're not going to be using rejection regions. And finally, another last thing here is the conclusion. And you should write out a nice conclusion in ordinary language so that your boss or the general public or whoever can understand what you're trying to say. Okay, so that is the ingredients. There's 5 steps, typically 5 steps in a test, a statistical test of hypothesis. So let's start looking at some examples. What we want to do now is to learn a little bit more about how to identify an alternative and a null hypothesis in a question. And one general issue with all of this is that it is hard to establish an alternative hypothesis. So what we're going to do instead is to disestablish the null hypothesis. So what we're going to work, for technical reasons, which I'll explain very soon, we're going to work mostly with the null hypothesis. And that will give us information about the alternative hypothesis. So it's just easier to work with the null hypothesis. And I will explain all of this in a second. So with that in mind, the language that we're using, when I say reject, that means reject the null hypothesis. Okay, so rejection means rejecting the null hypothesis. Accepting means accept the null hypothesis. Rejection, we're saying H0 is false. And acceptance, we say H0 is true. Right, so everything is relative to the null hypothesis. Then once we've decided what to do about the null hypothesis, then we will conclude or comment about the alternative hypothesis. But the language that we use is relative to the null hypothesis, rejection or accepting of the null hypothesis. So let's take a look at some examples from the textbook. So example 9.1, you wish to show that the average hourly wage of clerical workers in the province of New Brunswick is different from $14, which is the national average. So see, you're trying to establish something different about New Brunswick. You're trying to show that New Brunswick varies from the rest of the country. So that is our alternative hypothesis. And so we're going to write that out as the alternative hypothesis is that the mean wage is different from $14. So very often we'll be talking about means in this chapter and then the discrete version cousins. So the continuous version, we're going to talk about means. The alternative hypothesis is that the mean of a population is different from some fixed number, some fixed value, say 14. So the null hypothesis that corresponds to it is its logical opposite, that the mean in New Brunswick is $14. And so those two are really logical opposites in this case. And then if we said we reject, means we're rejecting the null hypothesis. And if we're accepting, and that means that that the mu is substantially different. Oops, that's supposed to say substantially different from 14. Otherwise, if our statistical test tells us to accept, that means accept the null hypothesis. And so in that case, mu is close to 14 within some margin of error. Okay, so that's how a hypothesis test would work in this case. And as a researcher, probably you want to reject. That would be nice if you can. But of course, you can't always reject the null hypothesis. But that's sort of what you're aiming for, because then, oh yes, you can publish, you can present it at conferences and say, there's something interesting about New Brunswick. All right, now let's take a look at another example. So we're going to look at example 9.2 in the textbook. A milling process currently produces an average of 3% defectives. You're interested in showing that a simple adjustment on a machine will decrease P, the proportion of defectives produced in the milling process. Thus, okay, so in this case, example 9, the first one here was 9.1. Here, example 9.2. Something different about this is that we're talking now about population proportions. And so example 9.1, that's a 1. 9.1 is continuous, and 9.2 is discrete. So that's one difference between 9.1 and 9.2. Now, let's see, we're making the adjustment to the machine, and we want to show that that results in less than 3% defectives. So that proportion of defectives is less than 3%. Remember, we're counting how many defectives there are, and that'll be x, but then x over n is the proportion of defectives, and that would be in a sample. But anyway, the population proportion, we're going to hope that it's less than 3%. And so that's going to be our alternative hypothesis. That's our hope. So its logical contradiction would be greater than or equal to the 3%, but that's not the way we have to work when we do hypothesis testing. So what we're going to have to do in hypothesis testing is just to stick with 3 equals to 3. So that makes this it's not quite the logical opposite that we had in the first one. But we're for technical reasons, we're going to have to use this equal sign in the null hypothesis. So the null hypothesis always has an equal sign. And I'll explain why that has to be in a moment. Oops, sorry. Okay, so that is this milling process example. So in this case, rejecting the null hypothesis would mean accepting the alternative hypothesis, and that's what we want to do. So again, we want to reject, but of course we have to do our statistical test to make sure that we can reject the null hypothesis. Okay, let's take a look at the next example. The next example is 9.3. The mean, according to Statistics Canada, the mean birth weight of newborn babies in Canada is 3.372 kilograms for both sexes. However, a pediatrician in Alberta believes that the mean birth of newborn babies for both sexes in Alberta is much higher than the national average. So in this case, we have a situation where it's a continuous variable. That's a weight. We're not counting, we're measuring in this case. So I'm going to use mu, and we're hoping, we think that it is greater than that number, 3.372. And so our hope becomes the alternative hypothesis. And again, the null hypothesis, we're going to make an equality there. Okay, so this is example 9.3. And this is a continuous example. Now let's give a quick review of the last 3. Here we were testing inequality versus equality. So those, that is the alternative hypothesis has a not equal sign in it. Over here we have a less than. The null hypothesis, the alternative hypothesis has a less than symbol. And in the last case, the alternative hypothesis has a greater than symbol. So those are really 3 different ways it can go. We can test for alternative has a not equal, has a less than, or has a greater than. And then the null hypothesis is always equal. So the alternative hypothesis can be any of those 3, and the null hypothesis always has to be equality. Okay, so example 9.4 in the textbook really doesn't add anything new. You can read it on your own. I'm just going to skip past it. Okay. When your alternative hypothesis has a not equal, it is called two-tailed. We will learn why soon. And when the alternative hypothesis has a less than or a greater than, it is called one-tailed. All right. Now, next, after we've discussed in great detail hypotheses. Now the test statistic. So let's take a look at again at this example from the New Brunswick clerical workers. So we had example 9.1. Let's review that again. We believe that the mean average, sorry, not the mean average, the mean wage for these clerical workers is different from $14 an hour. So it's different from the national average. So that became our alternative hypothesis. Now the null hypothesis is always equality, so that's that. Now, in order to test this hypothesis, we're going to need some actual data. And so somebody's gone out and gathered some data for us. They've gone through the records, found a random sample of 100. So that becomes the sample size is 100. And the sample mean is $15 an hour. Oh, I should have written 15 there. Pardon me. 15, gotta fix that. Okay. $15 an hour in the sample. And now people who are very bad at statistics or readers of USA Today or whatever would say, oh yeah, this proves that that the mean wage for New Brunswick workers is $15. Well, it doesn't, because it's only a sample. Our sample may not be representative. So we're going to have to do a little more work to establish, how likely this is to be representative and how likely it is to be different from 14. And as you know from chapter 8, in order to do that, we're going to need the sample standard deviation as well. And that, in this case, has been calculated by our researcher to be 2. And so this gives us all the quantities we need to calculate a test statistic. Okay, so the test statistic is just for most of what we're doing in this textbook, certainly pretty much most of chapter 9, we're going to be using Z statistics. Now that's not universally true. So we are going to look at a couple of other different statistics in the last 2 chapters we're going to cover. But but for now, I think we should become comfortable with using the Z statistic for almost everything. So the Z statistic is just a Z-score. And what we do is we take the sample mean, and from that we subtract our assumed mean. So we're going to assume the null hypothesis is true, and then we're going to divide by the standard error. And if you recall, a standard error is the population standard deviation divided by the square root of the sample size. And that is very close to right. So that's the test statistic that we're going to use. And in this case, let's do the calculation. So we had the sample mean was 15. 14 was the sample standard deviation. 14 was the 14 was the hypothesized population mean, and then the standard deviation, sample standard deviation was 2, and sample size was 100. So this is 1 over 2 over 10. That's 1 over 0.2, and that is 5. Okay, how does this work now? What does this tell us? Well, the idea is we're going to assume that the null hypothesis is true. So this is similar to an argument by contradiction. So, for example, in a courtroom drama, we may say, okay, Professor Giesbrecht, we're going to assume that Professor Giesbrecht did not commit the crime. And then what we're going to do is we're going to find some kind of contradiction in that. So that would be a mathematical argument by contradiction. So we assume something is true, and we would arrive at a contradiction as a result of that assumption. For example, another very simple example, I could assume that 3 is an even number, and then I could show that 1 is an even number, and then, well, I know that 1 is odd, so that can't be my assumption that 3 was even led to an absurd result, a contradiction. In statistics, we do something very similar, but not exactly the same. So what we're going to do is assume that the null hypothesis is true. And that gives us a very definite result, a value to use for the population mean. That's why our null hypothesis always has equality in it. So if we assume the null hypothesis is true, we have a definite value that mu has to be 14. So I use that in my calculation, and I got a z-score of 5. Now 5 is not impossible, so I don't get a perfectly logical contradiction. However, 5 is unlikely. How often do we see a z-score of 5? Almost never. It's extremely unlikely to see anything like that. The probability is so small, you have to go out to something like 5 or 6 decimal points to even write it down. So it's not in our tables, because our table would essentially give 0 for this probability. So it's not quite 0. But it's such a tiny number that we're going to say it's just so unlikely that something must be wrong. And we go through our assumptions. So we have all this data that we gathered. We're going to assume that this data was gathered correctly. So that's okay. We're going to assume that that's okay. All this theory that goes into the z-score and the normal distribution and so on, that's all mathematics. We're going to assume that that's all correct. So that's not the weakness in our argument. The only weakness in our argument was this initial assumption of the null hypothesis. So if we assume the null hypothesis and we get something that's extremely unlikely as a result, then there must be something wrong with the null hypothesis. And so this means that we're going to reject the null hypothesis. That gives us evidence that we can accept the alternative hypothesis and say that the average wage is different from $14. Right, so that is a kind of a bare bones outline of how this this test of hypothesis works. Now, 5, I kind of hand waved. You can't see my hands, but they are waving. I kind of hand waved my way through this through this argument about z equal 5 being high. But we want to quantify this, because we want to make all of this as definite as possible. We don't want to just say, oh yeah, 5 is too high. No, I want to know exactly how high is too high. So let's draw our number line, and here are all our possible values for z-scores. And suppose we do a sample and calculate the z-score for the sample. And suppose we're going to assume that the mean really is 14. And then our distribution will look like this. That's our sampling distribution will look like that. Now, we're going to say that it's too high when it's cut off by some critical value. Oops, and this is, sorry, this is not, there's x's and there's z's. So x is 14 and the z would be 0 here. Okay, so there's some critical value at which it is too high, or the z-score will be too high. What should that critical value be? Well, that depends on how confident we wish to be in our results. So we want to be, often we want to be 95% confident. This is kind of our usual. And we know that from chapter 8. We like to be 95% confident. So 95% confident means 95% of our measurements should be in this region. That means 5% should be outside of it, but since there are two tails, we're going to divide that into two pieces, 2.5% each. So 2.5% each. And if you recall, we can do a reverse lookup on our table, and so we find that the 97.5, so this is 2.5 plus 95 is 97.5%. We have a z-score of 1.96. And over here, we have a negative 1.96. And so if our z-score is in here, it's going to lead to acceptance of the null hypothesis. The z-score is close to 0, close enough to 0, that we don't see any real difference between the sample mean and the proposed population mean. It's not unlikely, so we don't. We've got a likely result if our z-score is in here. So it's likely that our null hypothesis is true. So we're going to accept the null hypothesis here. So we call this the acceptance region. Out here and out here, we make the assumption of the null hypothesis, but then get something that is unusual. And it's something that we would see normally less than 5% of the time. So in this case, we believe there's something wrong with our null hypothesis, and we're going to reject the null hypothesis. And so these two pieces here are the rejection region. Note that the rejection region has two parts corresponding to two tails. Right, there's two tails. Okay, so that would be a two-tailed test of hypothesis. So we're going to go into in more detail about all of this in the next section. So don't worry if it's a little bit confusing at this point. It should be a little confusing. It's all new. But I'm just kind of trying to give a high-level overview of how this is all going to work. And the last thing that I want to talk about is what if we're testing whether wages are higher than the national average. So what if we were interested in this? This is different from the previous example. So in the previous example, I did, oops, dash 14 is the number, I'm sorry. I tested whether it was different from 14. In this next example, I'm going to test whether it is higher than 14. That should be 14. Okay. So this is a different question. It really is a different question. The null hypothesis is always going to be equality, so it's going to be the same as previous. But we have to set this up differently. So in one-tailed test, the setup is actually going to look a little bit different. Oops, there we go again. The setup is going to look a little different. So in this case, I still have my sampling distribution. I've really messed up. I'm just, ugh. Okay. There. I'm not an artist. I think this is an art school. Okay, that is going to have to do. So there's my sampling distribution, and the mean, according to central limit theorem, is going to be at 14, and the z-score there is going to be 0. In this case, what we want to do is to show that we're 95% confident here. We have 95% is in this whole region. So that means there's a whole 5% up here. And so that has pushed this number down 1.645, if you recall. You should know that number from chapter 8. You should probably have these almost memorized at this point. But that has changed our the shape. It certainly changed the shape of the rejection region. The rejection region is now only got one piece to it. And the acceptance region is also got only one piece, but it's infinite now. And it's also changed the critical value. The number that divides the two, that separates the two regions, is now 1.645 instead of 1.96, which it was in the previous example. So we have multiple different changes. Just by making this single change here, we're looking for a mean that's now greater than, or we are hypothesizing a mean greater than 14 instead of a mean that's different from 14. We have a kind of a completely different looking hypothesis test. Right, so we will go through multiple examples in the future, so don't stress too much about understanding these particular ones. It's just the kind of features of these problems I wanted to give a quick overview of. And I wanted to show you that there is a big difference between the two-tailed test of hypothesis and a one-tailed test of hypothesis. All right, so those are all the major concepts. There's one other little thing, and that's the value alpha And we know this from chapter 8. This is called a significance level, which it was called in chapter 8 as well. But it has a particular meaning, and that meaning is clarified in chapter 9. So I'm not going to go into detail about that just yet, but keep an eye out for it. We're going to talk about it soon enough. That alpha has a very specific technical meaning, and so at the appropriate time later on in the chapter, I will give you the exact definition of alpha, and I think that'll help us to understand it better. All right, so that is it for chapter sections 9.1 and 9.2. That's really just an introduction to the idea, the concept of hypothesis testing, and we will get into all the details in the following few sections of chapter 9. So see you again soon.